All right, Alexis, what is it you want to learn about today?
Remember the time we were driving home from the city and you were talking about the adaptive cruise control in your car?
Yes, adaptive cruise control. Cruise control is actually pretty cool. But let's talk about what is cruise control first. So, cruise control has been around for a long time. It basically works similar to the thermostat that controls like our AC and stuff. But we have a car, and in the car is a computer chip. And this chip is going to do things like it's going to detect what our speed is, and it's going to be able to adjust the controls to try and maintain that speed. So I'm driving, and when I push the button, it tells the cruise control this is the speed I want to keep. Now let's pretend we're driving on a highway. The speed limit's 70 miles an hour.
So we'll go 75.
Yes, Daddy sets his cruise at 75 miles per hour. And so what happens is this chip is constantly monitoring the speed, and then if there's any changes, it's going to change the throttle. And the throttle it's usually sort of like a pipe, and there's a control in it. It controls how much air gets sucked in and how much fuel gets mixed in to the engine. It basically controls how much engine power it gets. Mm-hmm. And so if we're driving along and we, for example, start going up a hill, then this speed's going to go down, and the chip's going to recognize it, and it's going to say, hey, to maintain speed, I need more throttle. It's going to open up the throttle. It's going to suck in more air. It's going to spray in more fuel, and it's going to try and match this speed until we get over the top. And as we start going down,
oh my God, we need to slow down.
We need to slow down. So this speed's going to go up, it's going to go over, and it's going to say, hey, we're going too fast. Let's close off the throttle a little bit. We need less air, less fuel, and it's going to slow that down a little bit. So that's basics. I'm fairly certain that there's a little bit more complicated stuff going on up here in this chip.
In this Dorito?
Yes, in the Dorito. Because whenever I was young, my friends and I, we had a joke because there's a resume button. And the joke was that the resume button was actually the resume now button. So when you hit the resume button, it took you back.
You're still on a race.
Terrible at this game. It takes you back to the speed that you had previously programmed. But if you're not going very fast at all, when you hit resume, the engine just like this opens wide open. So I'm assuming that they have that they have tiers, right? So like if it's maybe like 0 to 5 miles per hour.
It's like tier 1.
Yeah, like you have you're allowed to control the throttle a certain percentage. But if it's like 6 to 10, maybe you can do more. And then if it's more, like I'll say, yes, you can have all of the throttle. And you can just open it wide open. So I imagine that there's tiers in there. That seems like it'd be fairly easy to code. So that if the difference gets really wide, the cruise control system is allowed to adjust the throttle to a greater degree. And then if it's smaller, then it just makes smaller adjustments just to sort of keep you within a couple miles per hour of whatever you set. So that's basic cruise control. If we want to have fancier cruise control, then we're going to add some cool aerospace technology to it. And that cool aerospace technology is radar.
Radar.
You've heard of radar before, right?
Yes.
So, that car is not near as good as the first one.
That's a hand-me-down car.
Yeah. So, radar stands for radio ranging and detection. Or no, radio detection and ranging.
Yeah.
Became popular in World War II.
That makes sense.
Yeah, the British did a lot of work with radar to keep the Nazis from bombing their cities. This one, I guess, is a pickup truck. It's got a sort of weird oblong shape.
Feels like a very good idea to try to prevent them from bombing your city.
Yes. So that was one of their systems to that aided them in the Battle of Britain. They would set up these radar stations, and they would help detect whenever there was fighters or bombers flying in, and they would scramble their fighters to intercept.
Did they win that battle?
Yes, they did. So in this particular case, we're going to use a similar technology. We're going to broadcast out a radio signal, and it's going to detect if there's a car in front of me. And the way that happens, so there's a couple different modes that radars can use. One of them is pulse, and what happens is, so it's going to send out a pulse wave or a radio wave, and it's going to hit this car in front, and it's going to reflect back. And our system that's listening for it is going to measure the time it takes for those pulses to go, because we know how fast these electromagnetic waves travel. They travel at a constant speed, and they travel pretty close to the speed of light.
That is pretty fast.
Yes. And so we have equations. You can actually look them up on the internet. It's pretty cool. Let's do radar pulse equations. Yeah, so you can actually have the equations, like you could go look them up for yourself, that figures out if you can measure the time between when this pulse is sent and when the reflection is received, what that distance is.
It's like scientific echolocation.
It is, right?
Yeah.
Yeah, instead of using sound, we're using a radio wave. And so one of the ways that adaptive cruise can work is it can measure this distance, and whenever you're approaching the other car, it also has a follow distance. And so when it's running the code, it's going to say, hey, if I get in within a certain distance, it's going to override our speed keeping, and it's going to reduce the speed until we can match whatever our follow distance is.
So we don't spy hunter ram the car.
Yes, without it, because cruise control doesn't know. And so yes, if you don't have cruise control, you will just spy hunter style ram into the back end of the car without any kind, if there's no driver input.
Oh.
But this radar allows the car to see what's in front of it, and it allows it to make an adjustment. The other thing that they can do is we can use what's called the Doppler effect. So you live in Oklahoma, you have heard of weather radar before, you have heard of Doppler radar before, right?
Yeah.
All right. So the Doppler effect is, we don't need a car yet. So whenever a wave is transmitted, the reflection can change based on if the object is moving forward or away, right? So the Doppler effect, the best example of the Doppler effect is if you are, like if you're on the side of the road and a car's coming by, the Doppler effect is what makes it do that. Yes. Because whenever you are the observer, if the source of the wave, whatever the wave is, whether it's a light wave, whether it's a sound wave, whether it's a radio wave, if the observer is, or if the source is moving towards the observer, then it sounds like the frequency is going up. Oh, okay, here's a good one. Perfect. So what happens is, okay, so we've got a car, right? It's a terrible car. It looks like a hat.
It looks like a hat.
We have this person over here. The car is putting out sound waves at the exact same frequency. It's not changing. But as it gets closer, it takes less time for the peaks of the wave to reach the observer. And so it gives the illusion that they're getting higher in frequency. And as they're moving away, it takes the peaks longer to get to the observer. And so it gives the illusion that it's decreasing in frequency. It's getting lower. And so that Doppler effect, they can measure that, and they can tell if something is moving towards or away, and they can measure the speed. So we use this a lot in astronomy because to measure planets and stars to tell if they're moving towards the Earth or away, and at what speed.
Some of them are moving like towards the Earth?
Well, yeah, relatively.
I was a bit confused. I was like,
They're not like hurtling towards Earth in a potential extinction level impact.
No, I didn't mean like that.
But yes, they're moving towards the Earth. If something is moving away, it's called a redshift. If it's moving towards, it's called a blue shift.
Blue shift.
Yes. So this red is when the wavelengths are getting longer, and the blue is when the wavelengths are getting shorter, higher frequency. So there's lots of uses for it, and in our particular case, we have a car, and if we use the Doppler effect in addition to our pulse, then we can not only tell, ooh, we can have a pink car apparently. Let's do a pink car. We can not only tell where or how far away this car is, we can get a reliable estimate on if it's moving towards us or away from us, and what speed it's moving based on how these wavelengths change when they're reflected back. And one of the cool things about that, like these equations are out just on the internet too. Like if you want to figure it out, equations, radar.
Oh, we're still on videos.
Yeah. But yeah, you can find the equations for how they are calculating the speed of a moving object based on the Doppler shift from that radio pulse. And so this allows us to do two different things that are very cool. So one is we can error check. So before we were just using a pulse to measure the distance, right? Because we know what time it takes. And if we have a memory function, we can measure the delta, which is change. It's not just a triangle. It's a Greek letter delta for change.
Okay.
So if we have a distance and that we can keep a memory of it, and we can say, hey, this distance is decreasing, we can do some math and we can estimate the velocity of this vehicle that's in front of us. If we're also using Doppler technology, we can do the equation, and we can, based on the frequency shift from our reflections, we can get another estimate of it, and allows us to just sort of double check our work to try and see how fast that car is moving.
Make sure we don't hit this car.
Right. Well, see, once we can do that, so we can estimate its distance, and we can also measure its speed. And then
wrote US.
Distance. And whenever we have those two things, it allows our cruise control system to make a more complicated decision on about how much we're going to adjust the velocity to avoid running into this car. So like if I'm going 75 and this one's going like 60.
You're 15 miles per hour ahead of this car.
That's a pretty big distance. And so, you know, it's really easy if you think about it as a coding problem. You have sort of branches. We're trying to maintain a speed unless we get something within a certain distance that we're also trying to maintain. And then we're also going to have our system make a decision that, hey, if the speed differential is so large, sort of like the tiers we talked about in the first one, like if there's a really big gap, then we want to make a big change to the throttle to try and avoid, and it's really, it's really not avoid contact. We're trying to maintain whatever this interval distance is that we've programmed in and set. So if it's like 20 feet, whatever we have to do to maintain 20 feet, right? And so if we have to ramp it down super slow, then we will. And if we have those two pieces of information, then it makes it we can make a much more complex decision about how we're going to adjust the speed versus if it only has the distance. The other thing this allows you to do, and why I think that they're doing these kind of things in the vehicle, I tried to find some technical manuals to get some more information about it after you ask about it the first time. But you can do collision detection or collision avoidance. So I have not tested it out to its extreme because I am not going to drive my car at a stationary object and, and see how much it wants to stop.
No!
But it will. So like we've got a rock.
It looks kind of like a termite hill.
Yeah, that's an interesting little thing. So if I'm going 75 and this is going 0,
Just sitting there.
Yeah, so this becomes a problem.
Well, yeah, you're gonna hit it.
So if our system can engage these different functions, it knows that we have a distance that's close, or a very short distance, and we have a very big differential between speeds. So now it's not just going to say, hey, I'm going to let off the gas. It's going to flash a warning at me. It's going to step on the brakes. It's not just trying to slow the car down and match whatever this interval distance is. It's trying to stop the vehicle. Because
it's going to hit the termite hill and they're going to eat your house.
Yes. They're going to eat my house.
It's revenge.
For destroying their home.
Yes.
They're going to follow back in my car and eat my house.
Yes. Doesn't sound so stupid. Okay, maybe he does, but I mean, could happen.
Yes, I'm sure there's automakers all over the world are going to put that in their brochure. Avoid your home being eaten, because our system will avoid you from running into termite hills. Do you have any other questions or silly comments that you would like to explore?
No.
Okay. You're good. So that was a good explanation of adaptive cruise.
Yeah.
Yeah. The important sciencey thing is the Doppler effect. Like, it does a lot of cool stuff, and that's how our weather radars keep us safe whenever it's storming and stuff.
The radars.
Yes.
Not the people. They get it wrong.
Yes. The weathermen, not super accurate, but the radar's pretty good. All right. So what do we say at the end of all our YouTube videos?
Like and subscribe.
Like and subscribe. All right. Good job, Alexis.
Thank you.